November 7, 1944, 2:37 p.m. The British Metallurgical Research Laboratory in Sheffield. Dr. William Harrison stared in disbelief at the test results of the captured German armor plating. The Brinell hardness test read 3/12 BHN, 312. His hand trembled as he repeated the measurement for the third time. The same result. The Krupp armor plating, salvaged from a destroyed Tiger II tank, was harder than anything the entire British steel industry had ever produced. The best British armor plates maxed out at 265 BHN, but that wasn't the most terrifying thing. When Harrison tested the plate for brittleness, it showed a toughness of 31 foot-pounds at -40 degrees Fahrenheit. Impossible. According to all known metallurgical laws, steel this hard should be brittle, shattering like glass at low temperatures. Yet this German steel combined both extreme hardness and exceptional toughness. Harrison wrote in his report, "The Germans have redefined metallurgy. We don't understand how." What Dr. Harrison discovered on that November day in 1944 would shape Western materials science for the next 3 decades. The quest to unlock the secret of Krupp steel became an obsession. Thousands of engineers, hundreds of millions of dollars, countless failed experiments. 30 years to decipher a German secret forged in the blast furnaces of Essen. Before Krupp, the story of armor plate manufacturing was one of compromise. Since the first armored vehicles of World War I, metallurgists worldwide had grappled with the same fundamental problem: hardness versus toughness. The physics seemed clear. To harden steel, you heated it to around 150 degrees Fahrenheit and quenched it rapidly in water or oil. This process, called quenching, created a crystalline structure called martensite, extremely hard, but as brittle as glass. A single hit could shatter such a plate, sending lethal fragments into the tank's interior. The alternative was softer steel, tough and ductile, but insufficient against armor-piercing ammunition. American, British, French, and Soviet metallurgists faced the same wall. They chose the middle ground, medium-hard plates with acceptable toughness. American armor plates typically achieve 250 Brinell hardness. Good enough against most threats, but only just. The Soviets experimented with thicker plates, compensating through mass rather than quality. The British developed surface-hardened plates, hard on the outside, soft on the inside. Each nation sought solutions within known boundaries. Then, war came to North Africa. February 1943, Kasserine Pass. American M4 Sherman tanks encountered German Tiger and Panther tanks. What followed was a massacre that sent American metallurgists into a panic. German 80mm shells pierced Sherman fronts from 1,300 yards. Conversely, American 75mm shells bounced off German armor like ping-pong balls. After the battle, American units salvaged fragments of German armor plating. The samples went to Aberdeen Proving Ground, Maryland. The initial tests shocked the experts. These plates weren't just harder, they were superior in every measurable way, and nobody understood how. The roots of this superiority lay in Essen, in the heart of the Ruhr region. Krupp AG, founded in 1811, had over a century of experience in steel production, but the breakthrough came not through tradition, but through meticulous science. In 1934, Dr. Edward Maurer, head of the Krupp Research Department, began an ambitious project, commissioned by the German High Command: develop an armor plate that exceeded all known properties. Maurer assembled a team of 47 metallurgists. They had unlimited resources, state-of-the-art equipment, and a clear mission: rewrite the laws of metallurgy. The team began with fundamental research. They analyzed the crystalline structure of steel at a microscopic level. They experimented with dozens of alloying elements: chromium, molybdenum, nickel, vanadium, tungsten, manganese. Each element affected the properties differently. Chromium increased hardness and corrosion resistance. Molybdenum improved high-temperature strength. Nickel increased toughness, but the combinations were endlessly complex. Too much of one element rendered the steel unusable. Too little brought no improvement. The Krupp team conducted over 2,000 experimental melts. Each batch was tested: hardness, toughness, tensile strength, fatigue resistance, weldability. Slowly, a picture emerged. The optimal alloy contained 0.42% carbon, 1.65% nickel, 1.58% chromium, 0.35% molybdenum, plus traces of vanadium and manganese. But the alloy was just the beginning. The real breakthrough lay in the hardening process. Maurer developed a revolutionary method: differential hardening combined with precisely controlled tempering. The armor plates were heated to exactly 1550 degrees Fahrenheit, held for 45 minutes to ensure uniform austenitization. Then came the critical step: quenching in oil with a controlled temperature of 140 degrees Fahrenheit. The cooling rate was crucial. Too fast created cracks, too slow prevented complete martensite formation. Krupp developed special oil baths with agitators to control the cooling rate precisely. After quenching came the secret: multiple tempering. The plates were heated 3 times to 1076 degrees Fahrenheit, each time for 2 hours, then slowly cooled in air. This process transformed brittle martensite into tempered martensite, retaining the hardness but dramatically regaining toughness. The result was extraordinary. Krupp armor plates reached 300 to 320 Brinell hardness, with a simultaneous impact strength of 30 foot-pounds at -40 degrees Fahrenheit. For comparison, American plates with 250 BHN only managed 16 foot-pounds. The German plates were harder and tougher. In 1938, Krupp presented the first plates to the German High Command. The field tests exceeded all expectations. At Aberdeen Proving Ground, the secret testing ground south of Berlin, the plates underwent rigorous testing. Firing from various distances with 37mm, 50mm and 75mm anti-tank grenades. The results were astonishing. From 875 yards, 50mm armor-piercing shells simply bounced off, leaving only shallow craters. Even 75mm shells from 550 yards did not penetrate the 3-inch Krupp plates. For comparison, they simultaneously tested French and British armor plates of the same thickness. These were penetrated. The German High Command officers were thrilled. Colonel Heinz Guderian, the later Panzer General, was present at the tests. He wrote in his report, "This armor gives our troops a decisive advantage. Enemy anti-tank measures will be ineffective. The psychological effect will be enormous." Krupp immediately received a massive order: 15,000 tons of armor plating for the new Panzer III and FE tanks. The production facilities in Essen were expanded massively. By 1939, the armor plating department employed over 3,200 workers in 3 shifts. The investment totaled 47 million Reichsmarks, an enormous sum for the time. When Allied intelligence received the first reports of superior German armor in 1943, a desperate race began. The Combined Intelligence Objectives Subcommittee, an American-British organization, made Krupp steel a top priority. Operation Ferrous, code name for the steel espionage, was launched. Agents in occupied territories received instructions: secure every fragment of German armor plating and send it for analysis. By the end of 1943, the Allies had collected over 200 samples. The systematic analysis began in February 1944, in 3 parallel programs: Aberdeen Proving Ground in Maryland, Sheffield Metallurgical Research Laboratory in England. and a secret Soviet laboratory in Chelyabinsk. The researchers started with chemical analysis. They determined the alloy composition using spectroscopy. The results were inconsistent. Different plates showed slightly different compositions, which confused the scientists. In fact, Krupp varied the alloy slightly depending on plate thickness and intended use, a refinement the Allies only understood later. But knowing the alloy was only the beginning. When the Allies tried to produce plates with an identical chemical composition, they failed spectacularly. The first American test batch in April 1944 achieved high hardness, but the plates shattered during firing tests. They were too brittle. British attempts in May 1944 produced tougher plates, but with only 270 BHN, far below German standards. The Soviet researchers had the same problem. The team in Aberdeen, under Dr. Robert Mayle, one of America's leading metallurgists, recognized the problem. The hardening process was crucial, not just the alloy, but how exactly did Krupp harden it? The captured plates revealed nothing. Metallographic investigations showed a homogeneous martensite structure, perfectly tempered. But how? The Americans experimented with hundreds of variations. Different quenching temperatures, water, oil, salt solutions, air, different tempering temperatures, 392, 572, 752, 932, 11 to 12 degrees Fahrenheit, different holding times, 1 hour, 2, 3, 4. The combinations were endless. Each attempt cost weeks and thousands of dollars. Most failed. An attempt in July 1944 came close, quenching in oil at 176 degrees Fahrenheit, followed by double tempering at 1022 degrees Fahrenheit. The resulting plate reached 290 BHN with acceptable toughness, better than previous American production, but still below German levels. And the Americans didn't know why. They had hit the target by chance, not through understanding what they didn't know. Krupp used triple tempering, not double. Krupp controlled the oil temperature to plus or minus 3.6 degrees Fahrenheit exactly. Krupp used special heating furnaces with a protective gas atmosphere to prevent oxidation. Krupp had decades of experience in process control. These details made the difference between good and exceptional. The frustration of the Allied engineers became clear in internal reports. A report from September 1944 from Aberdeen wrote, "We have replicated the chemical composition. We understand the basic processes. Yet, we cannot achieve the German results. There must be subtle process variables that we have not identified. The Germans have achieved a level of process control that our production facilities do not offer." A British report from October 1944 was more direct. German armor metallurgy is 10 years ahead of British practice. Without access to their production methods, we are essentially guessing. A Soviet report, later obtained through espionage, was the most honest. German armor plating shows a metallurgical perfection that exceeds our theoretical knowledge. Reproduction, impossible without complete technology transfer. These reports landed on the desks of top military leaders. General George Patton received a report on armor plating quality in November 1944. His handwritten note in the margin: "Why are we sending our boys into battle in inferior equipment? Fix this now." But it couldn't be simply fixed. The gap was too wide. Desperately, the Allies looked for shortcuts. If they couldn't replicate the steel, maybe they could steal it. Special Operations Executive, the British Intelligence Service, planned Operation Ferrum, a raid on the Krupp plant in Essen to seize production documents. The operation was planned 3 times and cancelled 3 times. Essen lay deep inside German territory, heavily defended. The risk was too high. The Americans pursued a different approach. They interrogated German prisoners of war, looking for Krupp engineers. In December 1944, they found one, Dr. Heinrich Müller, a young metallurgist who had worked at Krupp, under interrogation. Müller revealed some details: multiple tempering, controlled quenching, protective gas atmosphere, but Müller had been a low-ranking engineer. He didn't know the exact parameters. His knowledge was limited. Nevertheless, it gave the Americans new avenues to experiment. The financial costs of this desperate research were enormous. The American program to replicate German armor plating consumed an estimated $380 million between 1944 and 1950. Equivalent to over $5 billion today. Aberdeen Proving Ground alone conducted over 4,700 experimental melts. Each batch cost an average of $12,000 for materials, energy, and labor. Most ended up as scrap. Bethlehem Steel invested $89 million in new equipment, specifically for Krupp-like production. US Steel spent $67 million, Republic Steel another $43 million. The British expenses were similarly high. The Ministry of Supply budgeted £22 million for the steel research program between 1944 and 1952. The Soviet costs are harder to quantify, but estimates based on released documents suggest at least 2 billion rubles, a huge sum for the war-damaged Soviet economy. And despite these massive investments, it took years, even decades, to reach Krupp level. The superiority was brutally demonstrated on the battlefield. At Villers-Bocage in June 1944, a single Tiger I tank showed just how devastating it could be. Michael Wittmann, the famed tank commander, destroyed 14 British tanks and 15 half-tracks in 15 minutes. British reports after the battle documented: "Our 6-pounder shells bounced off the Tiger's frontal armor, with no penetrating effect. The Tiger showed no signs of damage." Similarly, in Normandy in August 1944, a lone Panther defended a crossroads near Mortain against American advances. It was fired upon by Sherman tanks from 3 directions. Post-war investigations counted 27 impact marks on the Panther's armor. Not a single one had penetrated. The Panther was only destroyed when American fighter bombers attacked it with bombs. As the war ended in May 1945, acquiring German steel technology became a top priority. Operation Paperclip, originally intended for rocket scientists, was expanded. Metallurgists were added to the target list. In June 1945, American troops reached the Krupp works in Essen. What they found exceeded their expectations. The production facilities had been heavily damaged by Allied bombing, but the technical archives were largely intact. Basement rooms filled with documentation, production logs, test reports, metallographic studies, process manuals. It was a treasure trove of metallurgical knowledge. Teams of American and British engineers scoured the plant. They found the special furnaces with protective gas atmospheres. They found the precisely controlled oil baths. They found records of thousands of experimental melts. And they found the engineers. Dr. Edward Maurer was interrogated in July 1945. Initially, he refused to cooperate. But with the prospect of war crimes trials looming, he became more talkative. In weeks of interrogations, Maurer laid out the entire story: the alloy development, the process optimization, the quality control. He drew flow charts, explained temperature profiles, described process controls. The Americans meticulously recorded every word. The resulting report, Technical Report 4489, Ferrous Metallurgy, German armor plate production, spanned 847 pages. It was immediately classified as top secret. Copies went to all major American steel producers: US Steel, Bethlehem Steel, Republic Steel, The Soviets, who held Essen in their occupation zone, systematically dismantled the production facilities. Entire furnaces were taken apart and shipped to Chelyabinsk. Over 200 German engineers and technicians were taken to Russia, some voluntarily with incentives, others under duress. The British secured patent rights and licenses, a less dramatic but valuable strategy in the long run. With this captured knowledge, the real work began, implementing German technology into Allied production. The implementation proved unexpectedly difficult. Having the theoretical knowledge was one thing. Reproducing it on an industrial scale was entirely different. The German processes required equipment and precision that simply didn't exist in Allied plants. American steel mills in 1945 were optimized for mass production, not precision. US Steel began a pilot program in August 1945. They installed protective gas furnaces, imported German measuring instruments, trained workers in the new procedures. The first production attempts in October 1945 were disappointing. The plates averaged 285 bhn, an improvement over previous American production, but still below the German standard of 310 bhn. The problem was process control. The temperature control in American furnaces was too inaccurate. Fluctuations of plus or minus 15 degrees Celsius were common. Acceptable for conventional steel, but deadly for the Krupp process. Krupp had achieved temperature control of plus or minus 2 degrees through years of optimization. Bethlehem Steel invested in new equipment. They bought German pyrometers, precise temperature measuring devices. They installed automatic control systems for the oil baths. Gradually, the results improved. By 1947, Bethlehem consistently reached 295 bhn. Better, but still not Krupp level. The Soviets made faster progress, but through a different approach. They replicated not only the technology, but the entire production environment. The German furnaces transported to Chelyabinsk were rebuilt, exact copies of the Krupp facilities. German engineers supervised the installation and operation. By 1948, the Soviet plant was producing armor plate with 305 bhn, nearly identical to the German standard. But the Soviets paid a price. Production was expensive and time-consuming. What the Soviet experience showed was this: the Krupp process worked, but only with German precision and process control. The British chose a pragmatic approach. They recognized that full replication was too difficult. Instead, they adapted elements of the Krupp process into their existing production. They adopted the concept of multiple tempering, but with British-adapted parameters. They improved their alloys based on German knowledge. The results were not spectacular, but solid. British armor plate consistently reached 280 bhn by 1950, a significant improvement over wartime standards. The full implementation of Krupp technology into Western production took not years, but decades. In the 1950s, American steel mills made gradual progress. New generations of production furnaces were built, designed with German precision in mind. Automation helped reduce human error. Computer-controlled processes, introduced in the 1960s, finally enabled the precise temperature control that Krupp had achieved manually. It wasn't until the mid-1960s that American plants consistently reached 300+ bhn on a production scale, 20 years after the end of the war. The M60 tank, introduced in 1960, used armor plate with an average hardness of 298 bhn. The M1 Abrams, designed in the 1970s, used further developed alloys based on Krupp principles, but with modern improvements. By then, the Krupp knowledge had been so completely assimilated that a new generation of engineers took it for granted. They often didn't even know that these techniques had been developed in Essen. Soviet tank production benefited enormously. The T-54-55, the most produced tank in history, used armor plate based directly on Krupp technology. Over 100,000 of these tanks were built. The armor was one of their strongest features, a direct legacy of German metallurgy. In the civilian sector, Krupp techniques found even wider application. High-strength steels for buildings, bridges, pressure vessels, all benefited from the principles developed in Essen in the 1930s. The oil industry uses Krupp-derived steels for deep-sea drilling, where extreme pressures push materials to their absolute limits. The aerospace industry adapted the concepts for titanium alloys and superalloys. The principle of precise heat treatment to optimize hardness and toughness became universal. Today, it's taught in textbooks, often without any mention of its origins. In 1975, 30 years after the war ended, the American Society for Metals held a conference on the history of armor plating technology. Several of the scientists who had analyzed German plates back in 1944 attended. Dr. Robert Mayle from Aberdeen Proving Ground, now an emeritus professor, gave the keynote address. He described the efforts of the 1940s, the frustration, the gradual progress. During the Q&A session, a young engineer from US Steel stood up. He asked, "Why did it take so long? We had the formulas, the process descriptions." Mayle smiled sadly. "We had the information," he said. "But information isn't knowledge. Knowledge isn't skill." The Germans had decades of experience, trial and error, an ingrained industrial culture. We were trying to replicate that in months. It was impossible. It took us a generation to really understand what they had done. Another participant, a former Soviet metallurgist who had emigrated to the West, added, "Even with German engineers, German equipment, and exact copies of their processes, it took us years to achieve consistent results." That just goes to show that technology isn't just hardware and formulas. It's expertise, culture, accumulated knowledge that lives in people. This discussion summed up the key lesson. Technology transfer is difficult, even when you know every technical detail. Krupp steel technology wasn't a single secret that could be stolen. It was a complex system of knowledge, skills, equipment, processes, and experience. The Allies captured the plans, but they had to relearn the know-how. This story repeats itself throughout the history of technology, from V-2 rockets to jet engines, from computers to optical systems. German technology from World War II set standards that took years to reach. The Krupp steel secret was just one example, but a particularly instructive one. These stories of technological superiority and the arduous journey to understand and replicate it are not just historical curiosities. They're fundamental lessons about the nature of innovation and technological progress. If you appreciate this kind of technical historical research, you can support this channel through YouTube. Super thanks. Every contribution allows me to delve deeper into archives, digitize rare documents, and interview eyewitness engineers before their memories are lost forever. Preserving these technical truths is important. They show us that technological progress isn't linear, that knowledge can be lost, that rediscovery sometimes takes decades. Your support helps to document these stories for future generations. Today, 80 years after those developments in Essen, metallurgy has moved on. Modern armor uses composite materials, ceramic layers, depleted uranium, titanium matrix composites. The days of homogeneous steel armor are over, but the principles remain. The idea of precise heat treatment for property optimization is more fundamental than ever. In the automotive industry, Krupp principles are used for high-strength, lightweight steels that make vehicles safer and more efficient. Modern cars use hardenable steels with tensile strengths of up to 1,500 MPa, far exceeding Krupp armor plating, but designed using the very same metallurgical concepts. In the tool industry, hardened steels are essential. Cutting tools, molds, precision instruments, all use heat treatment processes that have their roots in work like Krupp's. The oil and gas industry uses Krupp-derived technology for pipelines and drilling rigs in extreme environments. Arctic pipelines must remain tough at -76 degrees Fahrenheit. Deep-sea drilling requires steels that can withstand 14,500 psi of pressure. These requirements are met with modern alloys and heat treatments. But the fundamental concepts were developed in Germany back in the 1930s. The aerospace industry has translated these principles to new materials. Titanium alloys for aircraft structures are optimized with controlled heat treatment. Nickel-based superalloys for turbine blades, operating at 2,000 degrees Fahrenheit, use complex aging processes that are conceptually similar to Krupp tempering. Even in the electronics industry, there are echoes. Silicon wafers for microchips undergo thermal treatments to optimize their electronic properties. The precision is at the atomic level, but the concept, controlled thermal processes for material optimization, is the same. In 2015, a team of materials scientists from RWTH Aachen University published a study on historical Krupp armor plating. They used modern analytical methods, transmission electron microscopy, atom probe tomography, synchrotron X-ray diffraction. These tools can image the structure of steel at the atomic level, technology that was unthinkable in the 1940s. What they found was remarkable. The Krupp plates showed an extraordinarily homogeneous microstructure. The martensite laths were evenly distributed. The carbide precipitates perfectly sized and dispersed. It was as if the plates had been manufactured with modern computer-controlled processes, but they were handmade by workers who estimated temperature by color, who determined process times by experience. The study concluded, the quality of Krupp production demonstrates a level of craftsmanship and empirical knowledge that is rare in modern automated production. It is a testament to what human expertise can achieve. This expertise is largely lost. The engineers who possessed it have passed away. The industrial culture that nurtured it no longer exists. What remains are the principles, distilled in textbooks, codified in standards, embedded in modern processes. If you've listened this far, you've experienced a deep technical history. Which detail surprised you the most? Many viewers in the comments section share incredible connections. Grandfathers who worked in steel mills, company documents revealing German roots, modern patents that trace back to Krupp concepts. Your comments are often as valuable as the video itself, adding context, personal stories, and technical insights. Please share your thoughts. Every comment helps to bring this technical story to life, and if you'd like to see more of these detailed technical stories, let me know. The history of technology is full of these moments, breakthroughs that change the world, the painstaking processes of understanding them, the long-term impacts that we still feel today, from rockets to computers, from optics to aerodynamics. The technical legacy of the 20th century shapes our present in ways we often don't even realize. Telling these stories with technical accuracy and historical context is my mission. Thank you so much for listening.